All right. I don't know, what's your first computer game experience? But for me, it's definitely Super Mario. So, you know, it was like back to my maybe seven, and at that time, like I was like a super happy kid. Like every day I wake up, I go to school. I don't know why am I going to school. I listen to the lectures, and I don't know what to do. Sometimes I don't even. I'm not even aware that I need to turn in the assignment, like many of you maybe. Uh, but then at some point, some relative of mine, who is actually my auntie, and uh, so she invited me to her place, and I play Super Mario with my cousin, and I felt, oh, I really want to play this forever, right? That was the time that I first time touching Super Mario, and I found this is really fun. And then she said, okay, if you get like top three in your class, then I will buy one for you. And then I figure out, okay, if I want to get top three, I need to study really hard. I need to turn in all the assignment. And this is just the beginning of the semester, so I'm still having time to catch up. So at the end, I did get a third place. And I kind of like imply her that, hey, I got the third place. I got the third place. Oh, okay, good job. And and then I didn't get what I expected to get, right? I think a lot of you have that experience too, right? Your parents saying that, oh yeah, right? But that was the time that I was a really young child. So I'm thinking really positive in a way that, okay, I didn't get a gift. It's probably because the third place is just around the corner, so I'm not good enough. Then I study harder and harder, and so I become the first place. And then I became the first place in the rest of the 6 years as elementary school. I still don't get the game console that I want. So at the end I gave up. But that's why I'm here. So if I got good grades, it's must because of the Super Mario. But today, why we pull out Super Mario is because it's actually related to the content today in some sense. But before we start, yeah, I know you missed this slide, right? We talk about volume architecture. So volume architecture means that our computer should have processor and memory so that we can be reconfigurable. However, why is it reconfigurable? Because the magic here is that by loading different programs, by programs, it consists of two parts, instructions, which tells us what kind of operation you want the processor to do, as well as data, what data the processor should operate on. And by loading different programs into the memory, your processor will perform different combination of operations. And whenever you want to perform operations, it goes with the order where your processor has a spatial register called program counter, which actually indicates the location of your instruction in the memory. So, and after the lecture last time, you should know this program counter refers to the virtual memory address in your in your main memory. So internally, we need to go through a setup process, for example, TLB lookup. And if the TLB is a miss, we have to handle that miss. But once we figure out that translation from the virtual address to physical address, we should access the memory to get instruction. And then the processor should look into this instruction, figure out, okay, what instruction really want us to do, and then prepare the inputs for the target functional units, for example, an ALU, and then perform the desired operation, write the result back to the target register. However, there is also a special type of instruction called memory instruction. If that's the case, what you really need to do is that you still have to perform the ALU operations using the memory pipeline, and then after you figure out the memory address, you would have to incur an additional memory access. So that's the whole process. So the microprocessor itself is basically an implementation of the instruction set architecture defined by your computer. So in this way, the good thing about this kind of abstraction is that no matter what kind of processor you are using, from the software programmer's perspective, all we need to worry about is to write your program as C, Java, or Python. Internally, the compiler or the programming language runtime will translate your program into instructions that the processor should support. And regarding this, with the instruction set architecture abstraction, this is a contract between the hardware and software saying that, okay, the responsibility of the language framework is to generate a program that runs this instruction set architecture only. Any additional operation, I don't support. And then for the hardware perspective, I just try my best to support these instructions, and no matter how I make it happen, right? So so basically the microprocessor implements the instruction set architecture. So now I want to ask you a question before we talk about the basic processor design. So at UCR campus, like, where are you going for the lunch typically? Any reason why? I mean, if you are short on time, sure.
I have time. I'd like to have it. If I'm not, there's like sandwiches at Scotty's.
Okay, Scotty sandwich. Okay, and why? Just because of the time?
Yeah.
Okay, what else? Oh, really?
Yeah.
Why?
I find that usually when I'm short on time because I have some assignment or something to work on, so I work on it simultaneously.
Okay, so they have space, allow you to work on things simultaneously. What else? Panda Express. What's the reason?
I can just order on the app and then.
You can order it on an app. Okay. What else? I feel like every time when I have this lecture, I should have I'm doing commercials for those places.
So when I have the time, I'll actually walk all the way down to the UV and I'll get something from there.
Nah, what's good in UV?
Well, I just like eating at Mono Grill most of the time.
Okay. What else?
I get food in my own dorm. I just kind of like cook up something. Because usually some stuff I have is like they cook very fast.
I see. What kind of stuff will be really fast? Okay. Okay. What else? Okay, sounds like that's a typical option that people would have. I will show you later what I would choose. But we have talked about this, right? So it has been a period of time that a lot of people, well, a lot of companies started to test the ability of engineers using some tricky coding questions. And this is actually a set of questions that I grabbed from a website regarding the interview, and a lot of like I would say hardware companies especially, they like to test students regarding this set of tricky C or C++ programming languages. And the reason is right now a lot of firmware programs, they are written in C and C++. And in fact, although you think about like companies like Qualcomm or some other embedded system company, you think they are manufacturing the hardware. But in terms of their architecture, they are general purpose processors plus memory. And the only thing that differs their computer system from the software engineering, software companies' computer system is that their system typically won't run an operating system. So without operating system, what does that mean is that you are writing the so-called firmware program, which you directly compile your C code into a set of binaries, and there is no virtual memory support. You are using spatialized library to directly access the hardware resource. And because of that, you really need to know how to use memory pointers. You really need to know, and also their processors are kind of slow. So you really need to know how to optimize your program. So they like to test you C or C++ programming questions in a very tricky way to make sure that you understand how to use those interesting usage of pointers. So one of the very few questions that we showed before, so one of them is like swapping two variables in 5 different ways, right? So so right now, let's take a look of these tricky questions and see, are they really good? Are they really good? So this is one of the questions I want you to think about. All right, let's take a look. Okay, so looks like I like this. We need some discussion. So why don't you guys go ahead and talk to each other? All right, let's take a look. Okay, after discussion, more of you think the answer is B. So I want to hear about your thoughts. Why do you think it's not the right-hand side? First of all, right, most of you think it's either A or B, but not version B. Why is that? Because I tend to give you this kind of like counterintuitive example, or what do you think?
I'm assuming because there are two memory accesses for data inside, that's why A ends up being faster.
Okay, but if we have a reasonable enough compiler optimization, right, then there shouldn't be three. Do you agree? Because the data index is essentially the same thing across three, right? So a reasonable compiler optimization should incur only one. And this is something, if you went through your assignment, we probably should show quite a few examples of that, right? What else?
I think they're the same.
They are the same?
Because I mean.
So you chose E?
Yeah.
Okay.
But I think it's because, like we know memory access takes the longest, right?
Uh-huh.
So assuming they're both in DRAM, I think we can.
But are they going to be both in DRAM?
Okay, assuming it's an L1 then. If it's an L1 or a register, then I would say the throughput would still be limited by your mod operation. I think that would be the biggest bottleneck then. And by then I think you can still do the other operations in the same clock cycle.
Okay.
It will be the same.
Okay. Any other thoughts? For those of you who chose B. Right now, I don't hear any supporter of answer B yet.
I thought B was slower because you're doing more operations. You're shifting it by 4 and then you have to subtract it by data index again. Whereas in A, you just multiply the data index by 15.
Okay. So you are based on the fact that multiplication is faster than, is the same speed as shift and subtraction.
I think there's less instructions for multiplication.
Okay.
I assume just multiplying the number ones, then just accessing the data twice is less IC, like instructional count, from A to B.
Mm-hmm.
So I think B is faster. I mean, version A.
Yeah, but the thing is that don't forget, instruction count is not everything, right? Do you think the CPI won't kill you? Okay, so sometimes when you answer questions, right, you have to think thoroughly, right? Performance is always a combination of cycle time, which in this case, we can eliminate that. However, how about the CPI and IC? Right? So let's take a demo. Take a look at the demo. So this is the program which we show here, and let's run it and see what we got. So the first run, okay, version B is beaten by version A. The second run, version B again beaten by version A. Third run, version B again beaten by version A. So finally, version A always win, right? So let's take a look. Instruction count, indeed, right? It's lower, right? The CPI, the multiplication actually gives us higher CPI, right? However, reducing one instruction worth more in this case, right? So it's kind of interesting because a lot of people in the past thinking about if we could have replaced more complex instructions like multiplication with shift and subtraction, we are supposed to get better performance. But this one tells you, no, that's not the case, right? Why is that? Right. But for now, based on the demo, right, the answer is B. Instruction count is lower. That's the main reason based on what we learned from the stats. Now, You should also remember the demo, right? And when people talk about 5 different ways of swapping, right? And let me show you the demo again if you don't remember what's going on here. So here we have different types of swap. And I'm going to demonstrate it with flip array, which basically I traverse the array and then swap the last element with the current tail with the current head. So that's what the algorithm is doing. And let's see how the performance would differ. So again, as you can see, for the version A, which is the stupid version of the swap, right? Which a lot of interviewers would consider, you guys are stupid, right? If you write programs in this way. And as you can see, well, consistently, it outperforms the other version, right? So you can slam on the interviewer's head. Come on, this version seems to be silly, stupid. However, it's a lot faster than your smart version, right? Didn't you guys care about performance? Then you should try to think about our way, right? So why is that, right? And also, you remember this one, very counterintuitive from many people's perspective, right? Why am I adding a sort? Now, this time, I indeed increase the amount of instructions. Would that the whole program a lot faster, right? So if you don't believe, we can run the demo again. If I do I have the demo? Yeah, right, like this one, I can run the sorting and see. With sorting, it's only 0.15, and without sorting, it's 0.5, right? So those are the demos that I can show you that, okay, very counterintuitive. A lot of you don't believe that, right? But through this upcoming series, we are going to tell you the answer why. So today we are going to recap on the concept of a processor, the pipeline processor, the pipeline hazards, and maybe talking about structural hazards if we have time. So first of all, let's talk a little bit about what indeed a processor is. So through the recap that we had before, we already know the main purpose of the processor is to execute instructions. So what's the life of an instruction from end to end? What begins the life of an instruction inside your processor? Fetch from where? Where in the memory? Where in the memory? Where in the memory? There is something called instruction count, right? Sorry, instruction pointer, a program counter, right? Fetch an instruction from the memory at the position of your instruction pointer or program counter, right? And then what's the next thing to do? Decoding, what does that mean by decoding? Is it decoding? What's the meaning of decoding? So you have to figure out what functional units, what's the desired operation, and what are the operands. And then prepare your operands, for example, reading from source registers, and prepare the operands to the target functional units. That's the decoding, right? That's the decoding. What's the next? Is execution, right? Execution, depending on which instructions you are running, you may do things differently. So if it's an ALU instruction, you should perform ALU operations, for example, add, subtraction, multiplication. If it's a conditional branch instruction, no matter it's jump or a conditional branch, you always have to determine the branch outcome at this time, right? So you still need the ALU to do something for you. And if it's a memory instruction, that's a typical misconception that people would have. So we typically say, well, we are going to enter the memory pipeline. However, it doesn't mean that you don't do computation. Instead, you want to determine the effective address for data memory access. And then you perform the DRAM access or cache memory access. using the effective address that you just calculated. If there is a memory operation, data memory access operation. So once you are done, if this is an instruction that will modify a target register, for example, an LU operation, a read instruction, then you need to present the result to the target register. And finally, you update the program counter. So in the upcoming cycles, you can fetch the instruction at the right place. And when you update a PC, there are two rules. If you have a branch that is taken, that means that you are changing the direction of the PC. And if the branch is not taken, or if this is not a branch instruction, typically you will go to the next instruction. So for example, in 32-bit instruction set architecture like RISC, you are doing like PC plus 4. But for x86, it could be any number range from 1 to 17. So that's the thing. However, one misconception people would typically have is that a lot of people might think branch taken means the evaluation result is true. However, what really means by branch taken, it means that we are changing the direction of the next instruction. And that doesn't have to be true or false. So for example, you can easily come up with a few situations where you change your direction because it's false, right? So there is not really a correlation between truth and false, as well as branch taken, not taken, when you are writing your program. It's more about if the execution result of the branch would change your direction of execution. So for example, if it's a loop, it's taken because it's going back. However, if you are leaving the loop, which means that you are no longer staying in a loop, then it's actually not taken, right? So this is what really means by branch taken, not taken. So based on that, right, if I really want to design a processor, the very basic idea of having a processor, let's forget about everything. Right now you have a blank sheet and I want to design the processor from scratch, right? What's the first thing that I should do? Okay, have a memory, so I have cache. Okay, fine. What's next? Do we start from ALU? No, what do we start? Program counter, okay. So you should have a program counter. With program counter, then you know where to fetch the instruction, right? So what's next? Instruction decode, so you should have some kind of hardware unit that wires the instruction bits and figure out what to do. And there should be some kind of control unit, also have wires to figure out how to set the input of your functional units correctly. So only the ones that we want to use will be driven up, right? So what's next? LU? Can we directly operate on LU now? What ALU should rely on? Registers, right? So you need to tell the register file what kind of register values or where in a register file should I access, right? And then the registers will provide inputs and outputs, allow the functional units to perform operations. And as you can see, right, there is one thing that I kind of like make it clear is that for the memory part, I separate these two things, address generation and memory access. So you know, like for memory access at this time, we are not actually doing memory operations. We are just, sorry, for the memory access, that's the time that we actually waiting for the cache to give us the result. But at this stage, I'm just generating the address, right? So, and what's after? So if it's memory access, I will access data. Okay, what's after? You have to present your result in register file. And if it's branch result, you have to change your program counter, right? Are we done? Not yet? Right? Actually, we are done. So the basic design of this processor, right, is that the basic idea is that we just ran everything within a cycle, right? So every cycle, beginning from the cycle, I fetch an instruction all the way to the end. And then once I'm done, I go through the next cycle, the next instruction, right? And then finally, right? So it's pretty much like when I execute the instruction, right? The timing is pretty much like the following diagram in a way that, okay, for every instruction, I finish all the operations that I need for an instruction before I can proceed, right? So it's pretty much like you're going to a coffee shop, and a coffee shop has really one person, has only one person in a counter. And the person is also the blender for you. So what happened is that, okay, I want to order, I don't know how many of you went to Starbucks yesterday because of the Super Bowl free coffee, right? But if you go to a Starbucks at that time, people all want to redeem the free one. That's very terrible, right? Because like if there's only one person, what happened is that, oh, I want my free cup. Okay, show me that in your app. Oh, okay, I figured it out. And then the person would take your order and give you a tall like pike, right? And then go to that machine, press the button, and a few minutes, well, maybe just like a minute or two later, you'll get your cup. But before you get a cup, what about others? They have to wait until yours is done, right? So that's pretty much like this. That's pretty much like this, right? So none of the processor is doing things in this efficient way. Instead, modern processor, they take the approach called pipelining, right? And you know, there's a reason why we play Super Mario, because this is pipeline in Super Mario, right? They are basically pipeline workers, right? Okay, not fun. Anyway, so what's the concept of pipelining in computer architecture? So it means that we break up the logic into different stage of execution. And between different stage of execution, we have a so-called pipeline register, which would store the temporary result at the end of the cycle and fit it to the next pipeline stage at the beginning of the next cycle. So with this kind of circuit design, what we are able to do is that you can consider each segment of the processor is allowed to work on different instructions for different parts of the demand for each instruction simultaneously. So that's the idea of pipelining. So what does that mean is that with pipelining, in each cycle, so first of all, right, pipelining means that all the operation is only going through a stage in a pipeline. And separate pipeline stage would be led by different pipeline registers. So as you can hear, the clock signal is now connecting to the pipeline register. So what happened is that for the very beginning of the first cycle, assume there's nothing there, then only the first pipeline stage will be working on this red instruction. However, at the next pipeline stage, because the temporary result of the red instruction is right now going into the first pipeline register, so it will be advanced to the second pipeline stage. However, for the first pipeline stage, it will be free up for this yellow instruction. So if you can see, as we progress, at the end, every pipeline stage will be working on a different instruction. So you can pretty much imagine your timing diagram is going to be highly utilized. So right now I'm telling you, if I'm short on time, if I'm lazy to press the button of microwave, but I still want to walk outside, then I'm going to Subway. And the reason why I'm going Subway is because Subway is pretty much like a pipeline, right? Think about how you order in Subway, right? You line in the queue, and then the first people would ask you, what bread, right? So for me, I will say flatbread. Toasted? Sure. And then are you staying there? No, you are moved to the next person, right? And then you will hear on your right-hand side, there is a voice, what kind of bread, right? So it means that the attendee is right now working on another guest, another customer. And then some people will ask you what kind of protein, right? And then after the protein, what kind of vegetables, right? And then finally, register, checkout, right? So that's a pipeline. So regarding modern processor, you can pretty much imagine we can separate the operations in the following ways. So we can separate instruction fetch to get, with instruction decode, and decode will be together with registers as a single pipeline stage, and then all the ALU operations will be separated into another pipeline stage. And for memory operations, as we mentioned, it's more complex because you have to do address calculation plus memory access, so we should further separate it. And then the write back to the register, that will be another one, right? So that with that, what you could imagine is that in the first pipeline, in the first cycle, the purple instruction should only go through the first pipeline stage. And then in the next cycle, the first instruction will go to the instruction decode and register, and the second instruction will be fetched. And now, during the next cycle, the purple instruction will go to the LU, the blue instruction will go to decode, the green instruction will go to fetch, and then the upcoming cycle, you can see each of them will be occupying at a different pipeline stage, right? So right now, you can imagine this processor could be more efficient in a certain way. First of all, each cycle, we only advance to one pipeline stage. So a direct thing that we can imagine is that your cycle time is a lot shorter, because previously you have to wait the whole 5 or 6 things to be finished to get your cycle done. But right now, all you need is the longest pipeline stage that you have. And then you also have the parallelism, instruction level parallelism being executed, right? So that means that you are going to make your performance better, right? So if we use another representation of the execution, which is a timing diagram, you will see the horizontal axis will be the time, the vertical axis will be the instruction. So for the first cycle, I'm fetching the you can pretty much figure out that, okay, so this is a pipeline diagram. So you can see, well, after a certain point, every pipeline stage in the processor is right now working on an instruction. However, you also finish an instruction every cycle, right? What does that mean is that your CPI, cycles per instruction, in this case, a fully utilized pipeline, remains the same as a single cycle pipe processor, that every cycle you are done with one instruction, right? So your CPI is about the same, right? However, as I mentioned, because your cycle time is a lot shorter, so you actually get performance, right? So pipelining is actually allowing our processor to operate at a higher clock speed, or say a shorter cycle time, with the same or similar CPI to improve performance. However, because you are still running the same program, there shouldn't be any change in your instruction count, right? So previously, all mechanisms we learned, they would change both instruction count and CPI. However, this one, we only change the cycle time in an optimal case, right? So, but is it really possible that we can just change the cycle time without changing the CPI? So that begins with this example. All right, let's take a look. Okay, so, I love this figure because it means that we really need discussion. So why don't you guys go ahead and discuss with your friend.
Because there is a slight differentiate results because the way on the before you conduct the complete the operation, you start parsing
All right, so let's see. So, okay, so this is the result we have for now. But after the discussion, it seems like we are shifting toward the right-hand side, right? So let's take a look. So, what do you guys think? Any ones that you have in mind? Okay, what do you have in mind?
You're telling me to count the instructions that are
The pairs, right? How many pairs? Like what are pairs that you?
5 pairs. And the pairs are the XOR L with the add L.
Okay, so which number?
1 to 3.
Okay, 1 and 3.
You have
2 and 3.
You have
2 and 4.
You have 4 and 5, and then 5 and 6.
4 and 5. 5 and 6. What else? Other sauce? Two and 3? Yeah, we did. Okay, so for this kind of question, again, how do you tackle that? What to do? Okay, you draw a pipeline, right? How many of you really did that during your discussion? None. Okay. Again, don't be lazy, right? Draw the pipeline. So, at the very beginning, we fetch the first instruction. In the second cycle, can we advance the first instruction? Yeah. Okay, so it will be instruction decode. And then when we free up, we can fetch the next instruction, right? In the third cycle, can we continuously advance the first instruction? Yes. How about the second instruction? Can we advance that? Can we advance the second instruction to decode now? Can we fetch the third instruction? Okay. Now, in the fourth cycle, can I advance the first instruction? Can I advance the second instruction? Yes. Can I advance the third instruction? No, why not? I need to access the register. But how do I know if I'm accessing that register? You need to decode it first, and you know that there is such an issue, right? So you still have to advance to the next stage, right? So, okay, first of all, as long as the target functional unit is free, like nobody is using it, there's no reason why you cannot advance. The only reason why that you cannot advance is that I'm waiting for something to be certain, right? But for instruction decode, what's the input that you need? What are you decoding? Instruction itself, right? So for the third instruction, for the fourth cycle, do we have what we need? Yes, right? Because the instruction is fetched. So the next cycle, we still have no trouble. And then we are done with the first instruction. Is there anything because of first instruction that prevents us from advancing or generating back-to-back result? Right? So 1 doesn't create any hassle. Instruction 1 doesn't create any hassle for any later instruction. Now, for the fifth cycle, are we allowed to advance instruction 2, 2? How about the third? Why not? We don't, because the third instruction is actually waiting for ECX, right? So it cannot be advanced, right? So here, we also, there's another problem. Instruction 1 and instruction 3, they are competing on EAX, right? So that's another problem, right? And instruction 2 and instruction 3, they also have trouble, right? And even with that, the next cycle, I thought I can advance. However, another problem here. Both instruction fetch and data memory access, they need memory, right? And if we keep going, right? And also another thing which is easier to tell, 2 and 3, right? And if we keep going, right now the problem is 2 and 3, they are also competing on the same pipeline stage, right? And also, again, when we want to start this instruction, the value is not ready yet, right? And finally, if we want to fetch the next instruction after this jump not equal, we have to wait for the jump instruction to finish before we can fetch, right? So actually there are more than 5, to be honest. Well, there are 5 pairs, right? Like this 1 and 3, 2 and 3. 2 and 3 actually cost quite a lot, right? And then 2 and 5, right? And 4 and 5, and finally 6 and 7, or 6 and 1, right? So these are all pairs of instructions that prevent us from executing instruction back to back. So as long as you have trouble of making your instruction advance back to back, your CPI won't be equal to 1, which cause you have your performance not being optimal, right? So regarding the pipeline processor design, what really matters is that how can we make our performance as close as possible to the theoretical CPI, right? So again, we like taxonomies to figure out the cause of a problem. And we have seen that in cache problems. So same thing as pipeline execution, we also have 3 different types of hazards. The first type of hazards is structural hazard, meaning that we have resource conflict that cannot support simultaneous execution of instructions in a pipeline. So for example, you have two instructions, they are competing with the same hardware resource. One of them, and pretty much the later one cannot proceed. So this is called structural hazard. And control hazard means that we don't know. Another key to consistently generate output for instruction is that you have to consistently fetch instructions. However, if you have control hazard, means that I have no idea where my next PC is. I would have trouble fetching the right instruction. So that means that you are going to prevent your performance from getting closer to optimal, right? So that's called control hazard. And data hazard means that the instruction is waiting for a value to be generated from the pipeline, from an early instruction, right? So you can pretty much think about structural hazard is that I just don't find the target functional units is free, right? This typically would happen when you are looking for a parking spot. Sometimes you have to like circular waiting because there is no functional units, which is a target parking lot available for you, right? And for control hazard, it's pretty much, I don't know how many of you sing like professional sports, right? Sometimes your game has to be paused because we have no idea if this is an out or a save, right? So you have to wait for that to figure out before you can proceed, right? And then for data hazard, it's probably because the stuff that we have is still waiting, right? So now, based on our understanding about different hazards, can you tell me how many of them here are data hazards? All right, let's take a look. Okay, apparently we need discussion. So why don't you guys go ahead and talk to your friends for another 90 seconds.
Go for attempting to access AX. Isn't that structural hazard because they're both trying to access the register? Yeah. That one is the first one is
All right, let's take a look. Okay, so after discussion, more of you think the answer is 3. So, sorry, C, the answer is 2. So what are the 2 that you have in mind?
The data is not in ECX.
So which one?
The EX.
I mean, which pair?
Oh, the pair. The 2, 3, and 4, 5.
Say again?
2, 3, and then the other pair would be.
Okay, 2 and 3 on which register? ECX, right? And what's the other? 4 and 5 on RDI, right? So these are the 2 that we have data hazard, right? So, all right. So actually, right, like for this case, we have only 1 memory unit, but we have like 2 memory access requests at the same time. Don't forget, instruction also come from the memory, right? That's a structural hazard. And if both instructions are attempting to access EAX, don't forget, that's also a structural hazard. And if we don't know what's the next instruction to fetch, that's control hazard, right? So within this 5, 2 of them are data hazards, right? So that's the remaining ones, right? So now, take a look at this. What's the main reason do you think B is lower? All right, let's take a look. Okay, so most of you think the answer is B. Okay, so but why? Why is the answer B from your perspective? Why do you think it's B?
I think in the second option,
Mm-hmm.
line 2 depends on line 1,
Mm-hmm.
and then line 3 depends on line 2, so you have two dependencies.
Right, so here you have this kind of dependency, right? And because you have the dependency, they have to be serialized, right? How about the left-hand side?
There's only one dependency.
Okay, so there is only, well, there are actually two dependencies as well, right? However, because they are not, because this dependency, they are not back to back, right? So you are actually, and also because this chain is like, this is actually having a gap here, right? So it's, you get some more slack to resolve this data hazard, right? So that's why the left-hand side is typically better because of the lower data dependency. The data dependency is different, right? However, this optimization, like, why people in the past thinking about the right-hand side is a better code? If today I only have a single cycle processor, which is not pipeline, is there any difference in performance? If today what I have is a non-pipeline processor, is there any performance difference? Not really, right? Because they all require 3 statements, right? However, what's preferred in the right-hand side is that because you don't need any register. So if you have scarce register as the resource, then the right-hand side is preferred. That was true maybe 30 years ago, but not anymore, right? So there's a reason why people prefer the right-hand side. However, that's like your grandfather, right? Not in your age, right? That should be changed. Okay, so the takeaway here is that although theoretically pipeline is giving us better cycle time, which help us to get better throughput. However, 3 hazards: structural hazard, control hazards, and data hazard, prevent us from getting the optimal speed up that we want. So how to address those pipeline hazards? The universal solution is definitely just wait, right? Sometimes just waiting, then the problem will be resolved, right? What if I miss a deadline? Don't worry. If you keep waiting, the quarter will be ending, right? And then you don't have to resolve it, right? Just waiting. Sometimes the problem would resolve itself. So stalls, right? So like this case, whenever we have trouble, right? Like here, if we cannot advance to decode stage because we have a conflict in accessing register file, the later one should just wait, right? So what does that mean by wait? Is that we stay at the same stage without updating the pipeline register, so we are repeating the same stuff that we are doing here. And then the next cycle, yes, things are automatically resolved, right? We can advance, right? If that's the only thing. However, at this time, because we also have the data hazard, right? So we have to wait for longer, right? So as you can see, if you stall, what's the cost? You have to wait for a long time, which is not ideal, right? And people like me, we don't like waiting, right? We like to solve problems instead of waiting. That's why we are engineers, right? So if we want to solve problems, again, different problems, you have different ways to solve it, right? So for example, if I have a conflict between instruction decode and write back, which means that one instruction wants to access a register file with the same register, another instruction wants to update a register file with a target register. And if they are the same one, right? There is a structural hazard. So our solution is that it's actually taking a trick that register file is the fastest operation, one of the fastest operation in pipeline processor. So what we do is that on the rising edge, we update the value. We give priority to updates. And there are two reasons for that. Typically because the write back is at the last stage of an instruction. So what does that mean is that it must be the instruction go before needs to update. So based on the time sequence, we should let the early instruction go first. And another benefit is that if there is any instruction demanding on the output of the earlier instruction, then the later instruction can immediately receive the result in the second half of the cycle. Right? So that's why our solution would allow the first instruction, the earlier instruction to write, and the later instruction to read at the second half of the cycle. Right? So what does that mean is that for this sequence of instruction, we only perform the write back at the first half. And for the instruction decode, it would happen at the second half. So in this case, there won't be a conflict in resource. Another resource conflict occurs during the time of memory and instruction fetch, because both of them would require accessing memory, right? And we only have one unit for memory. So what's the solution? So in fact, we all know the solution already, which is the separated L1 cache, right? So a lot of you, and I intended to not talking about this when we talk about memory hierarchy, because the main reason why we want to separate it L1 instead of a unified L1 like what we did in L2 is simply because we want to make sure instruction fetch won't be affected by data access, memory access. So turns out we have a split L1 design, which allow smoother supply for your instructions, and also avoid the conflict between instruction fetch and the data memory access. So that's why we have a split cache design. So we have our memory hierarchy with separate instruction cache and the data cache. It's typically because we want to avoid the structural hazard. So right now you can imagine this is our processor. Now, another problem, right, is that some instructions, they don't use all the pipeline stages, right? And some instruction, they need more stages, right? So it turns out there might be a situation, some instructions, they would end up at the same situation. So for example, right now, if I allow this add instruction to directly go to write back, right, then both instructions will be at the write back stage. There will be a conflict in the register file. Oh, sorry, not the register file, the pipeline register. So this is not allowed, right? So what we end up should be doing is that we should make the later instruction stall. Or another thing which people would typically say is that every instruction should have exactly the same amount of pipeline stages. So this is another way of addressing that, right? And there is another problem, right? Another type of pipeline structural hazard is that, what if I have back-to-back memory instructions, right? Then again, the latency of accessing your cache is probably like 4 to 5 cycles, right? And you have to wait for the 4 to 5 cycles to finish before you can receive the next instruction. So what does that mean is that your next move instruction has to stall for 4 or 5 cycles, which is pretty long, right? So structurally, we have to also re-architecting our cache. So far, the cache we are seeing is a so-called blocking cache, meaning that when I access, right, I fetch a block until I have the block returned. There is no new operation could be received, right? And after I have done the current cache access, I can access the next part, right? That's the blocking cache. So another idea is, first of all, I divide the cache or memory unit into multiple banks. By banks, it means that each individual bank is a separate unit of receiving commands, and they can all perform their own memory operation. So I still have one cache unit, meaning that every cycle, I can only receive one request. However, if the request is different, is operating on a different target bank from the previous cycle, then I can concurrently issue that request to a separate bank. So even though there is a cycle, just one cycle difference, I don't need to wait for this bank to finish so that I can overlap some of the cache search time or access time with multiple. And what does that mean is that as long as the back-to-back memory instructions, their bank is not in conflict, we are in good shape.
Is this why the CUDA shared memory has the bank conflicts for the shared memory? Is it the same somewhere else?
Yeah. So with respect to that, what does that mean is that right now we can also make the memory access pipeline. We can also make the memory access pipeline, right? So right now you can imagine, okay, originally you thought there's many cycles that we have to wait here, but right now this part is also pipeline, right? So that's pretty much what we should see, right? So the takeaway for now is that we have 3 different types of hazard. However, for structural hazard, we have to fix it through more innovative hardware design. For example, the register file, we allow a single cycle to perform both read and write in an order. And we have split L1 cache to prevent the conflict between instruction fetch and instruction decode. And also we have multi-banked non-blocking cache to pipeline the access of memory, right? So these are all what we have so far, right? And also, right, if right now, if we have a memory design, right, that takes longer time, right? Right now, so again, as I said, right, you need to make sure that all the instructions to have the same length to avoid structural hazard, right? So that's another reason why in a conventional pipeline design, all instructions, they have the same pipeline, the same number of pipeline stages, right? Because they want to avoid structural hazard. Okay, so now, can you answer why, in this case, only instruction count matters?
Because you're limited by the mod operation.
Okay, so if every instruction has to go through the same number of pipeline stages, right, then you are pretty much, like every instruction would pretty much have a similar throughput. Similar will be delivered at a similar speed, right? So it turns out more instructions will be slower, right? If their latency are all about the same. Agree with that? Okay, so that's where we are before the midterm. So midterm will be online this Thursday. So just do it at your home, or if you want to come here, nobody would prevent you from doing that. If you want a separate place to do your midterm, right? But don't forget to bring your laptop. Assignment 3, and program assignment 2 due next Thursday. We do have another reading quiz coming up next Tuesday. And although we don't really consider the midterm as a real midterm in a way that it's counted the same weight as an assignment. However, I feel this is something that you still have to really doing it, because that will make you get a feeling regarding what kind of answers are preferable in terms of final, right? So this is like a practice for you so that you can adjust the way how you answer questions so that you can get better preparation for the final as well. So just make sure and make sure that you feel the time pressure, you feel the way how you answer the question, and feel the way how we give you feedback. Question?
Is there any, besides studying, of course, any other preparation we need before the midterm, or is it just like a quiz on Canvas?
I mean, review the slides. Okay, so if you want, I can attach this set of sample midterms. They are typically the questions that we have, right? And some of the stuff that my words going through. Sounds good? Okay.
Question was more like, because I know that professors who've done online midterms recently, they like do it through a special browser or something.
No, I'm not using that. It's just on Grayscope. Yeah, because for those stuff, I mean, if you really want to cheat, you can cheat anyway. Agree? Right? So I'm giving up on that. But other than that, enjoy the rest of your week. I would see you next Tuesday.